Hello everyone, welcome to lecture 4 of week 6 of the course Power Network Analysis, in which we continue our discussion on transmission line models and use of these models for performance assessment of transmission lines under different operating conditions. In today's discussion, we will continue with our long line model and we will discuss what is this lossless long line and what special attributes or features come out of this lossless long line model, and what are the notions of traveling waves, wavelength, etc., from the lossless perspective, and how it can lead to benefits in terms of analyzing the transmission network when it is struck by lightning, or for a DC network, how do we do DC fault analysis. That idea or notion I would try to give in. The previous lecture, we had our discussion on long line model, wherein we understood what the distributed parameters, how they are represented in a long line model. Every small minuscule section has a series impedance which is dictated by the line resistance and inductance, and has a shunt admittance which is dictated by the line conductance and capacitance. And we also understood two hyperbolic functions, those functions where cos hyperbolic and sin hyperbolic functions. So, a cos hyperbolic of let us say argument theta is nothing but e to the power theta plus e to the power minus theta by 2, where e is the exponential function, whereas sin hyperbolic of theta is e to the power theta minus e to the power minus theta by 2. And from here, can we get some beautiful equation? Because if we compare the actual trigonometric analogous functions, then cos square theta plus sin square theta is universally known to be equal to 1. Why is that? Again, there could be a straightforward reasoning to it. So, let us say if I have to take the exponential of j of theta, where j is square root of minus 1, the complex operator, then e to the power j theta is nothing but cos theta plus j sin theta. And similarly, if I take e to the power minus j theta, it would be cos theta minus j sin theta. Now, if I multiply both these equations, I get e to the power j theta minus j theta, which is essentially e to the power 0, is also equal to cos square theta plus sin square theta. The imaginary terms, they get cancelled because cos into sin has a negative sign here, whereas cos into sin has a positive sign here. So, the imaginary terms, they get cancelled. And we also know that j square is nothing but minus 1. So, that is how we get our sin square theta here. Since e to the power 0 is 1, so cos square theta, irrespective of the value of theta, it is always equal to, the sum is always equal to 1. So, on similar lines, can there be some relationship for hyperbolic functions? So, let's try out. So, if we find cos hyperbolic square of theta, it would be e to the power 2 theta plus e to the power minus 2 theta into 2 times of e theta and e minus theta, which results into only 2 divided by 4. And similarly, sin hyperbolic square theta would result into e to the power 2 theta plus e to the power minus 2 theta minus 2 by 4. If we now subtract sin hyperbolic square from cosine hyperbolic square, we have 2 minus 2 by 4, which is eventually equal to 1. And the way sec theta is equal to cos theta inverse, on similar line, hyperbolic sec theta is equal to inverse of cos hyperbolic theta also. So, we have sin square, cos square, hyperbolic square, cos hyperbolic square theta minus sin hyperbolic square theta is equal to 1, unlike cos square theta plus sin square theta is equal to 1. So, for the long line model, we had seen our V of x and I of x, where the Vx and Ix are per phase voltage and current measured from the sending end. Sending end is at x is equal to 0. And we have seen this relationship in the previous slide. If we divide this expression by cos hyperbolic square gamma x throughout, and rearrange terms, we would also get this term, the second equation. And in terms of boundary conditions, when they are placed, that is at x is equal to LL, we have VR and IR in terms of VS, IS, ZC. ZC is called as the characteristic impedance, which is also square root of small z and y. Small z is per unit series impedance, small y is per unit series admittance, and gamma is the propagation constant, which is usually a complex number, alpha being the attenuation constant, beta being the phase constant. It is equal to root over of small z and y. The unit of ZC is omega, which is ohm, and the unit of gamma is kilometer inverse. So with this, now let's go deep into the rest of the part of our discussion. So we have our VR, IR, receiving end voltage and current in terms of sending end quantities, the characteristic impedance and the propagation constant. LL is the line length measured from the sending end. So basically LL is the distance of the receiving end from the sending end. We can rearrange these two simultaneous equations and get VS and IS in terms of VR and IR. And the reason why I have mentioned this is that I wish to find or represent this long line model as a two-port network, wherein can I use the ABCD parameters, Z parameters, Y, H parameters as required. So if we recollect our ABCD parameters, then ABCD parameters are nothing but VS is equal to AVR plus BIR, and IS is equal to CVR plus DIR. If we compare these equations one to one in an analogous form, we have A, D equal to each other, and B and C they're in terms of hyperbolic functions of sine and ZC and etc. So still the conditions of symmetry and reciprocity hold true. Condition of symmetry is pretty obvious because A and D are equal. Condition of reciprocity, how it becomes obvious? Thanks to our previous discussion we had, where we are making use of this particular relationship. So here we have A into D, which is nothing but cos hyperbolic square gamma LL, which is nothing but AD, and BC, if we multiply ZC get cancelled, we still have sine hyperbolic square gamma LL. Cos hyperbolic square gamma LL minus sine hyperbolic square gamma LL is equal to 1, and that's how AD minus BC is always equal to 1, which reflects to the condition of reciprocity. Similarly, the ABCD parameters, they can be used to find the other parameters, other two-port parameters, wherein again conditions of symmetricity and reciprocity are still valid for Z parameters. Similarly, we have our Y parameters, wherein the discussions which we had in terms of medium line model are still applicable. The corresponding hyperbolic functions, they can be evaluated. Here, cot hyperbolic refers to inverse of so cot hyperbolic of theta is nothing but 1 by tan hyperbolic theta, which is also equal to cos hyperbolic theta divided by sine hyperbolic theta, because tan hyperbolic theta is sine hyperbolic by cos hyperbolic, and minus cosec hyperbolic is where the cosec hyperbolic, also in short written as CSCH theta, that's also an acceptable terminology, is nothing but 1 by sine hyperbolic of theta. Similarly, the H parameters can also be evaluated, where sec hyperbolic, we have already discussed what actually it is, which is nothing but inverse of cos hyperbolic. So conditions of symmetricity, reciprocity, they are all valid for all two-port network parameters. And these parameters, they are likely to be complex numbers, no matter whether they are H, Y, Z or ABCD, because ZC, gamma, they are also complex numbers. So corresponding hyperbolic functions would also turn out to be complex numbers. So what we have here is that we have our complex ABCD, Z, Y or H parameters obtained for a long line. Then is it not possible to come up with the nominal pi model the way we had for medium line, nominal pi model, nominal T model, rather than always solving differential equations or trying to evaluate these complex hyperbolic functions? Is there not a simpler representation or a nominal representation of long lines similar to medium line model? Yes, it's possible. Inspired by the medium line model, it is possible to draw a per phase circuit equivalent representation of a long line model in terms of nominal pi model or the nominal t model. The nominal pi model is pretty convenient and commonly used because of the way the shunt elements appear at the line ends, whereas in T model, the shunt element appears at the midpoint of the line. The pi model would have a fictitious series branch or a series impedance, whereas this impedance, when we are marking, remember in medium line for pi or T model, we had assumed lumped representation. In long line, the representation of parameters is distributed, it is not lumped. So when we are trying to find the equivalent nominal pi model or T model, the corresponding models refer to lumped representation. So the lumped parameters that would come in, they would not be the actual line impedance or admittance, they would be the fictitious quantities which nominally represent or capture the effect of the actual line. They are not the actual representation. So we would have a fictitious series impedance, we would have a fictitious series admittance or impedance which would take care of the capacitance effect. The equivalent lumped parameters, how can they be evaluated? Since we know the ABCD parameters for the actual long line, we also know what the ABCD parameters would be for a nominal pi model. So we can do reverse engineering, compare the ABCD parameters and find these equivalent fictitious series impedance and shunt impedance. Such a representation would actually be very useful for steady state and dynamic performance analysis, specifically for power flow analysis or the fault analysis or stability analysis, which would be the next part or the next few modules after this current module. And that's the reason why the nominal pi model is to be evaluated for a long line also. So in order to do that, we go back to our actual nominal pi model where we mark Z dash and Y dash to be those fictitious series impedance and shunt admittances. In nominal pi model, half of shunt admittance appears at the line end. The terminals, however, they refer to the same terminals of the actual long line. We are not making any approximation or modification of the terminals. We are only trying to represent the distributed form of line parameters in long line by using lumped representation of nominal pi model, where Z dash and Y dash are yet to be evaluated. So Z dash is the actual equivalent series impedance, Y dash is actual equivalent fictitious line admittance. In terms of ABCD parameters, not please, when those of you who are viewing this for the first time, please refer to the previous video, previous lecture, where you will be able to understand how do we get these equations of VSIS in terms of VRIR. In fact, these VSIS equations, they are coming by applying KVL across sending and receiving end, and by applying individual KCLs at these nodes. That's how we get three equations. Those three equations, when rearranged, rewritten, they can be written in terms of A, B, C, D parameters, which are functions of Z dash and Y dash. So from here, we easily know that A and D, they're nothing but 1 plus Z dash Y dash by 2. B is simply Z dash and C is Y dash 1 plus Z dash Y dash by 4. We also know what are these ABCD for the actual long line. So if we put those numbers, we would have sufficient number of equations to find our two unknowns Z dash and Y dash. So if we do that by one-to-one comparison of results, we would get ABCD or Z dash Y dash to be of the form where Y dash by 2 is tan hyperbolic gamma LL by 2 by ZC. And similarly, Z dash could also be evaluated over here using the B parameter, which is ZC into sine hyperbolic gamma L. Actual distributed representation gets represented as a nominal pi model, equivalent fictitious nominal long line model with Z dash and Y dash as the fictitious series impedance and admittance respectively. This same representation would be extensively used in power flow analysis and fault analysis as well as stability analysis. So coming to the other aspect of understanding or rethinking what these equations look like. Recollect that for a long line model, we have v of x as a1 into e to the power gamma x, where gamma is substituted as alpha plus j beta, and the general form of equation also had the term a2 into e to the power minus gamma x, where gamma is alpha plus j beta. J, again I would reiterate, is the complex operator, which is square root of minus 1. And using boundary conditions, we can also find what are vs, vx, ix, etc., etc. So given this, we are just trying to rethink, okay, is there any other interpretation involved behind these equations or solutions? Yes. Recollect that gamma is alpha plus j beta, which is square root of z of y. Z and y, they are made up of series resistance, inductance, conductance and capacitance, which are usually positive numbers. So it is expected that the individual complex numbers, the real and imaginary parts, they would have their separate parts as positive numbers. So usually alpha would be positive in actual transmission line, which is the usual case. So if alpha is positive, then e to the power alpha x would increase as x increases, whereas e to the power minus alpha x, which is appearing over here, it would decrease as x increases. So that's the notion, because alpha remains positive. Similarly, beta is also usually a positive number, and remember, e to the power j beta x, where j is square root of minus 1, can be written as cos of beta x plus j sine beta x. And if we want to take the mod value of this complex number, the mod of e to the power j theta is always equal to 1. Reason? Cos square theta plus sine square theta is equal to 1, where e to the power j theta is cos theta plus j sine theta, which we discussed in the second slide in this today's discussion. So as beta increases, which is usually, beta is positive, which is the usual case, e to the power j beta x and e to the power minus j beta x, which are sitting over here in this context, they would have the same magnitude, which is equal to 1. What would they otherwise do? They would create phase shifts in terms of beta x radians as x increases, or they would retard the corresponding voltage signal or voltage wave by j beta x as x increases for the other term. So if this is appreciable, if this is acceptable, the way alpha and beta, they are usually positive, and e to the power alpha x increases with increase in x, e to the power j beta x increases the phase angle, not the magnitude of the signal strength. So if we now look at the individual terms, so let's say if we focus on the second term, where v of x was having this as its second term, which was a2 e to the power minus gamma x, then as x increases, which means that we are moving away from the sending end and trying to reach the receiving end, since with increase in x, e to the power minus alpha x would decrease, that means the signal strength or the value of a to the power e to the power value of a2 into the power minus gamma x, it would start reducing, it would diminish, because alpha being positive, the signal strength is being attenuated and its phase would also start retarding. Similarly, for a1 into the power alpha plus j beta x, which is a1 into e to the power gamma x, we would have that as we are moving away from sending end to receiving end, the first term will have increase in signal strength and the phase angle would advance rather than retarding. Alternatively, we can also correlate these functions or interpretation as the phenomena involved behind traveling wave in still water. If a pebble is thrown in a pond having still water, then the point from where the pebble is thrown, from there waves start appearing, and as these waves move away from the point of disturbance or the point where pebble hit the surface of the water, the wave's strength start diminishing as they move away from the center where the pebble had sort of struck or the surface of water. This is very exactly to the phenomena involved behind this wave, a to the power a2 into the power gamma minus gamma x. So in a way, if the second term of v of x, if it can be called as the incident or the forward wave, then the first term of v of x can very well be called as the reflected or the backward wave. Incident and reflected waves, or these terminologies, they become very common in lightning analysis of transmission networks, whereas forward and backward waves, they are also pretty common, but often they are not used. I mean, they are used in context of lossless phenomena, but not oftenly used in context of DC fault analysis and etc. So the way we understood V of x terms, A1 and A2 terms having forward notion and backward notion, the way they're representing similar to the traveling waves in still water, similar notion can also be applicable for current waves. And that is what gives the indication that the power which is transmitted from sending end to receiving end through long lines, it doesn't always have to be a current signal or a voltage signal in time domain. They can also be interpreted as waves flowing through the transmission line, and that's how power receives the receiving end or the load end. So if we come to our focus of today's discussion, which is the lossless long line, how come lossless long line can they exist? Yes, usually transmission lines, they are designed to amplify or act as corridors for high voltage power from source end to load end, so that the corresponding I square loss are as low as possible. So by proper design or by good design, transmission lines do have very small resistance, and for sake of analysis, simplicity, discussion, if we were to consider for time being that this resistance is very negligible, which is actually the case, or not actually, but very close to the reality, that actual resistance is very small compared to line inductance. And we also know that conductance is difficult to model, so if we were to consider it to be negligible for practical purposes, then small z, which was actually r plus j omega L, where r tends to 0, would simply result in z being j omega L. And similarly, y, which was g plus j omega c, g was the conductance. If this tends to 0, we have y as j omega c. With this j, z and y now being defined, if we now find our constants like the characteristic impedance, propagation constant, they simply become functions of small l and small c, where small l is per unit line inductance and small c is per unit line capacitance. The attenuation constant becomes 0 because there is no loss in the network, so there would be no diminishing of the corresponding waves. In fact, if z and y, they are pure imaginary numbers or pure complex numbers, then their product of z of y would be j square omega square LC. The product itself does not have any real component, so the square root would also not have any real component. That's why alpha is 0, means there is no attenuation, so it is actually referring to a lossless condition. Beta becomes omega root over of LC, and our hyperbolic functions, which were these forms, they simplify to pure transcendental functions, the cos and beta, cos and sine functions. Again, remember, j is square root of -1. So if we write the Vx and Ix expressions for lossless long line, yes, gamma is replaced by simply j beta, cos and sine hyperbolic reduced to cos and simple j sine beta. So our V of x and I of x functions can be written from the usual long line model that we observed. And for this lossless long line, again we can find the corresponding ABCD parameters. We can find the corresponding nominal pi model, resulting or using the second boundary condition, where at x is equal to LL, V of x is VR and I of x is IR. In fact, interestingly, if we put x is equal to 0 into the first equation, then it becomes V of x is equal to Vs cosine of beta into 0 minus j is zc sine of beta into 0. Beta into 0 is nothing but 0. Sine of 0 is always 0. So essentially the second term goes away. And cosine of 0 is 1. So we have V of x is equal to V of s. Similarly, if you put x is equal to 0 in this equation, your I of x at x is equal to 0 would be simply I of s. Please verify that. So on similar lines, we can find the ABCD parameters z, y, h and nominal pi model for the lossless long line also. That is not our point of focus as of now. So we have our Vx and Ix equations for lossless long line, where the terms present here are still in phasor domain or frequency domain. These equations or closed form solutions can be represented or analyzed or stated in time domain, where they would pertain to certain traveling wave equations similar to traveling wave in still water. It would appear that the associated time domain voltages and currents in a lossless long line, they appear to be waves starting from sending end, they are reaching the receiving end, from there some reflection is happening. So again we have reflected wave, the way waves originate and propagate in ocean or sound in air, etc., etc. So such a model is actually the basis or premise behind ultra-fast transient analysis, which is a separate module of discussion in itself. Those of you who are interested or eager to learn about ultra-fast transient analysis, please refer to higher level postgraduate courses where you would find details of this. But the premise behind that analysis starts from this lossless long line, where the waves or the voltage and currents are being treated in terms of waves. So let's see how this traveling wave model looks like for a lossless long line. I'm just going to briefly state how do it appears, or why does it appear. So what I have here is a similar long line where the resistive components or conductive components are 0. So our small z, it is simply reduced down to j omega L. And here we are trying to find the solutions of the corresponding equations, not only in terms of x, but also as a function of time. So here the representation that I have here is the time domain representation, not the frequency domain representation. Vs, Vr, Is, Ir, they refer to the time domain quantities. They could be instantaneous quantities as well. And before I go deep into this discussion, if I have an inductor whose inductance is, let's say, L, and across this inductor I apply a voltage source, let's say the voltage source is V of t, and I want to find what is the expression of current through this inductor in time domain, then the basic property or governance of inductor states that the voltage drop across this inductor is nothing but first derivative of the current through the inductor multiplied by the corresponding inductance. Similarly, for capacitance, we have current through the capacitor is nothing but first derivative of voltage across the capacitor multiplied by the corresponding capacitance. These first derivatives, I di by dt and dv by dt, I'll represent them as L of I dash t, and this here I'll represent as C of V dash t. Those V dash and I dash terms mentioned over here essentially refer to these derivatives only. And since these derivatives can exist in terms of time, exist in terms of distance from the sending end. So if I take a cross section of the line section at a distance x from the sending end with width being delta x, and I choose similar nodes, node A, node B. At node A, I have to find what is V in terms of x and t. I want to find what is I again in terms of x and t. In the long line model where we had phasor representation, time was not there. Now time signal or time variable is also coming in, and I'm choosing A and B as my nodes. So can I derive an appropriate model for this lossless long line in terms of traveling waves? So yes, we have our single phase lossless representation with distance x measured from the sending end. And if I apply KVL across node A and B, where capital L here is nothing but small l, which is the per unit line inductance, then I have at node A voltage as V with a voltage drop of the drop across this inductor. So small l is the actual per unit line inductance. The width of section is delta x, so I multiply L into delta x, that gives me the overall inductance. And by the property which I mentioned over here, the voltage drop across this inductor would be L into delta X, partial derivative of current with respect to T. That is what is the term present over here. I'm starting from node A, trying to move along node B, flowing along the direction of current, so the corresponding voltage drop is negative. And eventually I reach this particular new voltage, where again V dash is the partial derivative with respect to X. Since this is the derivative of V with respect to X, if I multiply it with the section width, I would get the new voltage. So if I rearrange terms here, I have the equation which is resulting over here. V gets cancelled and I have this equation. Similarly, if I apply KCL at node A, I'll get my second equation, which is again obtained from similar lines. And if you correlate or oversee these two equations, they look more or less analogous to the long line model in phasor domain. The difference here is now we have the variable for x, the distance, as well as the variable for time t. So let's look at it in a but detailed manner. So if we reorient these equations and rearrange them, we get two unique differential equations, partial differential equations, one in terms of voltage and the other in terms of current. At the outset, these two equations look very similar to each other, and the way we had general form of expression or solution for long line model, on similar lines we can have our general form of expressions or equations for these two partial derivative equations also. So above equations, they are actually pertaining to travelling wave equations for voltage and current in a lossless long line. A generic form of solution for a voltage travelling wave, same for current, can be written in terms of V of x of t, which is equal to F1 of phi, where phi is ut minus x. I still have to define what is small u. Please have patience. I'll get back to you or get into those details in the next few slides. So phi is ut minus x, and general form of solution can be in terms of F1 phi. I can have also a separate form where I have F2 phi, where phi is some function of this signal, where phi in this F2 case becomes ut plus x. Okay, so I have a general form of solution for this voltage travelling wave, and consequently if I substitute these expressions into this analogous equation, let's do that. So what I have is, if I choose v of xt as f1 of phi and I want to take the first derivative with respect to x, then I would have del f1 phi with respect to x, which is also equal to del f1 phi with respect to phi using chain reaction or chain products of partial derivatives into del phi by del x. Since since phi is ut minus x, the term which I have defined here, so del phi by del x will become equal to minus 1. So I have minus f1 phi by del phi. Okay. Similarly, if I now take the double derivative, which is del square v by del x square, what I would get? I would get the same steps, they are shown over here. Del v by del x is minus del f1 by del phi. If I take one more derivative, then I would have minus del f1 phi by del phi with respect to entire del x, which can be rewritten as minus del square f1 phi by del x square into del phi by del x. Del phi by del x is equal to minus 1, minus gets cancelled, and that's how I get the second equation. On similar lines, I can take the time derivatives, arrive at the final time derivatives, and now if I compare these two equations, what do I get? Del square v by del x squared is LC times of del square v by del t square. That means u square should be equal to LC. Similar to the propagation constant that we had in terms of z and y, now we are getting a u constant. This u is called as the electromagnetic wave speed constant, travelling wave constant, and its unit is usually meters per second, where beta is the actual phase constant. Remember, beta was nothing but root over of, it was actually omega root over of LC. So if I divide beta by omega on both sides, I have root over of LC, which is nothing but u square. Sorry. So this is nothing but this is nothing but equal to u. So that's how I get u as omega by beta. Omega is 2 pi f, the phase angular frequency divided by beta, which is phase constant, and the unit becomes meter per second. Remember, omega is 2 pi f, unit of f is hertz. So actual unit of omega is second inverse. Beta doesn't have a unit in itself, its unit is meter inverse or kilometer inverse. So omega by beta is second inverse defined by meter inverse, which is meter per second. That's how u is called as the speed or velocity of some form. It's actually the electromagnetic wave propagation constant. Similarly, if I take the second wave f2 phi, where phi is ut plus x, that can also serve as a solution for this closed form solution. And the beauty here is f1 wave is actually called the forward wave, where f2 is called as the backward wave. Why? For forward wave or in f1, if t increases, then for f1 to remain constant, where f1 phi has to remain constant, the corresponding x should also increase, so that overall phi remains constant. Remember, phi was ut minus x. If t has to increase for phi to remain constant, x also has to increase. As time progresses, x increases. That means we are moving away from sending end, reaching towards the receiving end, and that's why we call it f1 wave to be the forward wave. Similarly, for f2, as time increases, x has to decrease so that ut plus x remains constant, and hence f2 value remains constant, and hence it is moving away from receiving end to sending end, called as the backward wave on similar lines. As per slide 12, which we have seen in the previous few sets, gamma is propagation constant is pure imaginary number. So if we plug in those values of v of x into the corresponding numbers here, we get e to the power j omega t in terms of time domain form. We get these as our closed form solutions for v in terms of x and t, where r1 and r2 are two analogous constants similar to be obtained from a1 and a2 using boundary conditions. Since ut minus x wave corresponds to the forward wave, so second term is called as the forward wave, similar to f1 ut minus x, whereas the first term, for it to remain constant in terms of magnitude, if t increases, x has to go down, so the first term is called as the backward wave. So that's the reason why these voltage expressions or current expressions can be considered similar to traveling waves in transmission lines. Since voltage and current in lossless line can be interpreted as waves, so if a wave can exist, definitely a notion of wavelength can come in, a notion of velocity can come in, and etc. etc. So in typical layman's perspective, wavelength is nothing but the distance traversed by a sine wave between two adjacent zero crossings or points which are separated by a phase difference of 2 pi radians. So since we know what is the phase constant beta, we know what is the angular frequency, we know what is the velocity of the wave, which is omega by beta, we can define its corresponding wavelength also, which is 2 pi by beta, 2 pi coming in because we need a zero crossing difference of 2 pi radians. Beta is a phase constant, so we get lambda as 2 pi by beta, which is nothing but 1 by f root over of L by L into C. Similarly, u is called as the velocity of electromagnetic wave propagation. If we were to evaluate this for actual transmission line, this value of u would appear to be very close to the speed of light in vacuum, and lambda would be in the order of few thousands of kilometers. That means if there's a transmission line and it is energized from the sending end, it would hardly take any time to reach that energy or power from sending end to receiving end, because as we know, the waves are traveling close to the speed of light. So that's the reason why when we turn on or turn off a particular switch, the corresponding appliance gets immediately on or off, which is hardly perceivable to the human eye. The delay involved is not there. So the energy or power, it flows through transmission lines at the speed of light, close to the speed of light. And on the other hand, we also say that current can exist in transmission line because electrons are flowing. So that means if power or energy has to be transferred at the speed of light, does it mean that the electrons are also flowing at the speed of light? Definitely no. Einstein's theory of relativity would indicate that if a matter, which is electron is also a matter, material, if it is moving at the speed of light, then the electron will no more remain as the electron, it would become energy. So actual electrons, they don't flow at the speed of light, they don't travel at the speed of light. What they actually do is they dissipate, or they uh, vibrate around their mean position in the transmission line. That's how the waves are created. That's how the electric field and magnetic fields are created. And actual speed of electrons, which is also known as the drift velocity, it's hardly few meters per second, whereas u is in the order of 300 power 8 meter per second, which is close to the speed of light. So actual electrons, they don't move, they only dissipate at the rate of drift velocity, which results in creations of electric fields and magnetic fields, which lead to resulting inductance and capacitance. And thanks to this inductance and capacitance, we get our waves traveling at close to speed of light, and that's why human eye cannot perceive any delay in transfer of energy or power from sending end to receiving end. Likewise, we can have our attenuation constant, we have already seen, to be 0 for a lossless line. We can have our beta in terms of root over of LC to pi f. We'll conclude this discussion with an example where I have considered a long line with series impedance defined. The total line length is not given. The total capacitance or shunt admittance is also given. And the line is delivering 40 megawatt power at 220 kV on the receiving end. At 0.9 power factor lagging, we have to find the sending end voltage current. We have to find the sending current for 220 kV when there is no load at the receiving end. So we know what is Z and Y, capital Z and capital Y. These are not the lumped parameters. These are the actual distributed parameters multiplied by the line length. From there also we can find our corresponding characteristic impedance, where we would have capital L as LL, the line length, which is not mentioned here. So from there we can find ZC. LL is the total line length, which is not given, and it is also not required, because essentially for hyperbolic functions we need gamma L, not just gamma. So we can directly find gamma L by root over of capital Z and capital Y, where capital Z and Y are the total fictitious series impedance and admittance in the distributed form. So if you find gamma L, Z and Y, they being complex numbers, so gamma L is also a complex number. This is the rectangular form of representation, whereas this is the polar form of representation. Please cross check these numbers, okay? And we can also find the corresponding exponential form of gamma L. Those of you who have calculators which can directly find the cos and hyperbolic functions, they need not do this step. But for others where hyperbolic functionality is not available, you have to evaluate e to the power gamma L separately, e to the power minus gamma L separately. And remember that in gamma L we have a real part, we have an imaginary part. So e to the power, so actually 1.0458, the term which you are seeing here, it is nothing but e to the power 0.0448, whereas 20.8327 degrees is nothing but 0.3636 radians converted into degrees by multiplying with 180 by pi. Please cross check that. So this you have to carefully evaluate. This is again polar form. We can rewrite it as rectangular form. We can also take the inverse of the first term and get it by minus gamma L. Take the means of the gamma L and the minus gamma L terms, you get cos hyperbolic function, the corresponding sin hyperbolic function. You have to be careful in evaluating that. It depends on what setting you have chosen in your calculator, whether it is in radian mode or degree mode, this number would drastically change. You have to be very careful. Once you know the corresponding hyperbolic functions, characteristic impedance, find ABCD parameters. Receiving end voltage we choose as a reference. So voltage is known, power is given, power factor is given, so we can find the corresponding complex power, then we can find the corresponding receiving end current. Plug in those ABCD with VR, IR, we get the sending end voltage, the corresponding sending end current, and the no load sending end current also for IR equal to, let me cross check. So our second bit of question was find sending end current for no load at receiving end. When there is no load at receiving end, IR becomes 0. That means there is no load. So voltage is still 220 by root 3 at the receiving end. And here we have C as this term multiplied by VR, and D remains same. The receiving end current I is 0, so IS is this particular term. Now that indicates that even if there is no load at the receiving end, the sending end current is non-zero and it is almost leading the receiving end voltage by 90 degrees, which indicates that the line is consuming reactive power or playing a lot with reactive power, which is the reason why line is still demanding for sending in current, although there is no load at the receiving end. The next lecture, we will take up the discussion based on today's discussion for surge impedance loading, which is related to the characteristic impedance, and also understand how complex powerful expressions can be evaluated in lossless long line, or lossless or lossy long line. And these complex power flow expressions that we would find or evaluate, they also have a lot of similarity with the capability curves of synchronous generators. Thank you.